Section: Introduction. In this section, we discuss the impact of BERT's release, which led to encoder-only transformer models becoming the standard in many natural language processing (NLP) applications. While large language models (LLMs) like GPT and Llama have gained attention, encoder-only models continue to be favored for various non-generative tasks due to their efficient processing capabilities and balanced performance relative to their size. These models excel in information retrieval (IR) tasks, such as semantic search, and have sparked renewed interest in their use alongside LLMs for tasks like classification and natural entity recognition (NER). Despite their effectiveness, many current pipelines still rely on older models, often using the original BERT, which presents several limitations, including a maximum sequence length of 512 tokens and outdated architectures. Additionally, the training data is often limited and lacks diversity, particularly in programming-related contexts. Recent efforts to modernize these models, like MosaiC-BERT and CrammingBERT, have focused on improving training efficiency but have not fully addressed the broader issues. We introduce ModernBERT, a revamped encoder-only transformer model designed to enhance performance and efficiency, especially for longer sequences. Our model is trained on a massive dataset of 2 trillion tokens, including code data, and we provide 2 versions, ModernBERT Base and ModernBERT Large, which achieve state-of-the-art performance across various tasks while processing sequences of 8,192 tokens, nearly twice as fast as previous models. To facilitate future research, we also release a modular architecture framework called FlexBERT, which allows for easy experimentation. Our architectural improvements include disabling bias terms in most layers to allocate more parameters effectively, using rotary positional embeddings for better context handling, and implementing a pre-normalization block to stabilize training. For efficiency, we alternate attention mechanisms between global and local attention, employ unpadding to eliminate wasted computation on padding tokens, and utilize flash attention for optimized memory and compute efficiency. Additionally, we leverage PyTorch's compilation features to enhance training throughput. Section Summary. In this section, we discuss the evolution and continued relevance of encoder-only transformer models in NLP, highlighting their efficiency and effectiveness in various applications, particularly in information retrieval. We introduce ModernBERT, a new model that enhances performance and efficiency by leveraging advanced architectural improvements and training on a vast dataset, achieving state-of-the-art results across multiple tasks. Section: Model Design. In this section, we discuss our model design. We observe that models with narrow layers, which we refer to as deep and narrow, learn differently compared to those with fewer wide layers, known as shallow and wide. Our findings indicate that deep and narrow language models perform better in downstream tasks, although they do have slower inference times. We also note that significant runtime improvements can be achieved by designing models with hardware considerations in mind, a point that many practitioners have informally recognized. We designed ModernBERT through various small-scale tests to optimize its performance on common GPUs while maintaining a deep and narrow structure to minimize inference delays. The base model has 22 layers and 149 million parameters, while the large model has 28 layers and 395 million parameters, balancing performance and hardware efficiency. The base model features a hidden size of 768 with an expansion of 2304, and the large model has a hidden size of 1024 with an expansion of 5248. These configurations allow for effective use of tensor cores and efficient processing across different GPU architectures. More details on our model design can be found in the appendix. For our data, both ModernBERT models are trained on 2 trillion tokens, primarily in English, sourced from web documents, code, and scientific literature. We selected the final data mixture through a series of tests. Instead of using the original BERT tokenizer, we chose a modern byte pair encoding (BPE) tokenizer, specifically a modified version of the Olmo tokenizer, which enhances token efficiency and performance in code-related tasks. Our tokenizer maintains compatibility with the original BERT model by using the same special tokens and templates. To optimize GPU usage, we set the vocabulary size to 50,368, which is a multiple of 64, including 83 unused tokens for downstream applications. To manage batch size variance during training, we implemented sequence packing using a greedy algorithm, achieving over 99% efficiency and ensuring uniform batch sizes. For training settings, we adopted the Masked Language Modeling (MLM) approach from ModernBERT, removing the next sentence prediction objective to reduce overhead without improving performance. We set the masking rate to 30%, as the previous rate of 15% was found to be less effective. We utilized the stable AtomW optimizer, which enhances AtomW by incorporating Artifactor-style update clipping for learning rate adjustments. This method proved to be more effective than standard gradient clipping, leading to more stable training. Details on hyperparameters are available in the appendix. During pre-training, we employed a modified trapezoidal learning rate schedule, known as Warm-Up Stable Decay, WSD. This schedule includes a brief warm-up period, maintains a constant learning rate for most of the training, and concludes with a short decay phase. We found that this approach matched the performance of cosine scheduling while allowing for continuous training without cold restart issues. We trained the ModernBERT base model at a constant learning rate of 0.0008 for 1.7 trillion tokens after a warm-up of 3 billion tokens. For the ModernBERT large model, we used a learning rate of 0.0005 for 900 billion tokens following a 2 billion token warm-up, rolling back to 0.00005 for the last 800 billion tokens after the loss plateaued. Our batch size scheduling began with smaller accumulated batches, gradually increasing to the full size. This approach accelerated training progress, with the batch size for ModernBERT base increasing from 768 to 4,608 over 50 billion tokens, and for ModernBERT large from 448 to 4,928 over 10 billion tokens, ensuring each batch size had the same number of update steps. More details are in the appendix. We initialized ModernBERT base with random weights using the Megatron method, while ModernBERT large's weights were initialized from the base model, following the Phi model family. This strategy consistently yielded better training results and sped up the initial loss reduction. After training on 1.7 trillion tokens with a sequence length of 1024, we extended ModernBERT's context length to 8,192 tokens by adjusting the global attention layer's rope parameter. We trained for an additional 300 billion tokens, starting with a lower learning rate of 0.0003 for 250 billion tokens on an 8,192 token mixture of the original dataset. We then upsampled higher quality sources and conducted a decay phase with a 1 sqrt learning rate schedule over 50 billion tokens. This context extension process resulted in a well-balanced model for downstream tasks, as using only one of these strategies in our tests led to performance losses in either retrieval or classification tasks. Section Summary. In this section, we discuss the design of ModernBERT, which utilizes a deep and narrow architecture to enhance downstream performance while maintaining hardware efficiency, and we detail our training methodology, including the use of a ModernBPE tokenizer, a modified learning rate schedule, and context length extension to optimize model performance across various tasks. Section: Downstream Evaluation. In this section, we conducted a comprehensive evaluation of ModernBERT across various tasks to showcase its versatility in typical scenarios. We compared ModernBERT with existing encoders of similar sizes. The base size, which has fewer than 150 million parameters, includes models like BERT base, DeBerta v3 base, and Roberta base, along with newer models like NomicBERT and GTE and MLM base. The large size, defined as having between 300 million and 500 million parameters, includes BERT large, DeBerta v3 large, Roberta large, and GTE and MLM large. For natural language understanding, we use the GLUE benchmark, which assesses how well models perform on various sentence understanding tasks, such as sentiment analysis and language entailment. Although GLUE is often seen as saturated with top-performing models, it remains a key evaluation tool for smaller models, giving us a good sense of their performance on common classification tasks. We followed previous studies by conducting a hyperparameter search on each GLUE subset to ensure our values were comparable to other models. In the realm of text retrieval, we focused on information retrieval, a common application for encoder-only models, where they help represent documents and queries for semantic search. This area has gained traction with the rise of large language models, LLMs, which use lightweight models for relevant context in retrieval augmented generation pipelines. We evaluated models in both single-vector dense passage retrieval, DPR, and multi-vector Colbert settings, reporting results using the NDCG at 1.0 metric. For each setting, we performed a learning rate sweep based on benchmark results to select the final model. For single-vector retrieval, we used DPR, where a single vector represents an entire document. We calculated the similarity between a query and a document using distance measures like cosine similarity. We fine-tuned each base model with the MS Marco dataset, employing mined hard negatives on 1.25 million samples with a batch size of 16 and a learning rate warm-up for 5% of the training. In multi-vector retrieval, we followed the Colbert approach, which avoids losing information by representing each document with its individual token vectors. We used the maxsim operator to compute similarity between queries and documents. Our training setup was based on JA-Call-BERT EV 2.5, with a batch size of 16 and a 5% learning rate warm-up, distilling knowledge from a teacher model using KL divergence. For long context text retrieval, ModernBERT, with its native 8192 context length, outperformed most existing encoders. However, standardized benchmarks for long context retrieval and encoder-only models are limited. We demonstrated improved performance on the English subset of the MLDR benchmark, which includes over 200,000 long documents. We evaluated 3 settings. 1. Single vector, out of domain. Models trained on short context MS Marco were evaluated on long context MLDR without further fine-tuning. 2. Single vector, in domain. Models trained on MS Marco were fine-tuned on the long context MLDR training set before evaluation. 3. Multi-vector, out of domain. Colbert models, due to their token-level maxsim mechanism, generalized to long context without specific training, and we evaluated the best checkpoints without additional fine-tuning on MLDR. Section Summary. In this section, we conducted extensive evaluations of ModernBERT across various tasks to showcase its versatility, comparing it against existing encoders of similar sizes using benchmarks like GLUE for natural language understanding and NDCG at 1.0 for information retrieval. We also highlighted ModernBERT's superior long context performance, particularly in retrieval tasks, despite the lack of standardized benchmarks for encoder-only models. Section: Code Retrieval. In this section, we discuss code retrieval, which has gained traction due to improved code completion models and the rise of code assistants. We utilize encoder-only models to handle and retrieve vast amounts of code-related information efficiently, emphasizing the need to assess and enhance the coding capabilities of these models. Unlike earlier encoders that primarily focused on text, ModernBERT is pre-trained on code and employs a code-aware tokenizer. To evaluate programming performance, we test all models on Code SearchNet, where the task is to find relevant documentation for code snippets, and Stack Overflow QA, where the goal is to identify suitable answers to questions. This hybrid evaluation involves both text and code, with Stack Overflow QA requiring the handling of long contexts, averaging 1,400 words for queries and 1,200 for documents, resulting in token counts exceeding 2,000. We use the CoIR framework for these evaluations, treating them as single-vector retrieval tasks, and all models are trained using the best hyperparameters identified earlier. We present aggregated results in a table, following standard practices for reporting average results on the GLUE evaluation suite. Detailed results can be found in the appendix. In terms of performance, ModernBERT stands out as the best model in both base and large sizes, showing significant improvements over the original BERT and RoBERT models across all tasks. For short context retrieval, both versions of ModernBERT outperform existing encoders in DPR and Colbert settings, including newer models like GTE and MLM and ModernBERT. While ModernBERT base slightly surpasses GTE and MLM base in DPR evaluations, ModernBERT large maintains a lead despite having fewer parameters. In long context retrieval, ModernBERT performs well in the DPR setting on MLDR tasks. Interestingly, without long context fine-tuning, it outperforms shorter context models and ModernBERT but falls short compared to GTE and MLM. The performance gap narrows when evaluated in domain, suggesting that ModernBERT can handle long context sequences effectively but may need more specialized tuning. We plan to investigate this further, considering factors like local attention and the pre-training budget. In the Colbert setting for long context retrieval, all long context models outperform short context ones by at least 40 points on NDCG at 1.0 without specific fine-tuning. ModernBERT leads among long context models by at least 9 points on both sizes. We believe these gains may stem from extensive pre-training and a beneficial interaction between local attention and Colbert-style retrieval, which we will explore in future work. Both ModernBERT models excel in natural language understanding, as shown by GLUE results. ModernBERT base outperforms all existing base models, including BERT v3 base, making it the first MLM-trained model to achieve this. ModernBERT large is the second best large encoder on GLUE, closely following BERT v3 large while having fewer parameters and processing tokens faster. In programming tasks, ModernBERT excels in both code-to-text and longer context hybrid settings, outperforming all other models. This was anticipated since it is the only evaluated encoder trained on a mix of programming data. These results indicate that ModernBERT has a better understanding of code without compromising its ability to process natural text. To assess inference efficiency across various sequence lengths, we create 4 synthetic sets of 8,192 documents. The first 2 sets are fixed length, with one containing 512 tokens and the other 8,192 tokens. We also create 2 varying length sets based on a normal distribution centered on half the maximum sequence length, with 256 and 4,096 tokens, respectively. We evaluate all models based on the number of tokens they can process per second, averaged over 10 runs, using a single NVIDIA RTX 4090 GPU. We also evaluate the GTE and MLM models in 2 settings, out of the box and with library enhancements for efficiency. Section Summary. In this section, we evaluate ModernBERT's performance on code retrieval tasks, demonstrating that it outperforms existing models in both short and long context retrieval settings, thanks to its unique training on code data. Our findings indicate that ModernBERT excels in understanding programming tasks while maintaining strong natural language processing capabilities, making it a superior choice for code-related applications. Section Results. In this section, we present the efficiency results measured in tokens per second, with detailed runtimes available in the appendix. We find that ModernBERT is the most efficient model overall. For short contexts, it handles fixed-length inputs of 512 tokens faster than all recent encoders, although it is slower than the original BERT and RoBERT models. In long contexts, ModernBERT outperforms all other encoders, processing documents 2.65 times and 3 times faster than the next fastest encoder for base and large sizes, respectively. When we look at the processing speed for an input length of 8,192 tokens, ModernBERT large achieves 46,801 tokens per second, which is quite close to GTE and MLM base at 47,507 tokens per second, but significantly faster than GTE and MLM large at 16,532 tokens per second. For variable length inputs, both GTE and MLM and ModernBERT are much faster than other models, primarily due to their design. However, ModernBERT is still more efficient than GTE and MLM, processing 14.5 to 30.9% more tokens per second at shorter context lengths and 98.8 to 118.8% more at longer lengths, thanks to its use of local attention. Additionally, we observe that ModernBERT is the most memory-efficient model across both sizes. ModernBERT base can handle batch sizes that are twice as large as those of other models for both input lengths. While ModernBERT large is slightly less memory efficient than the original BERT large for short contexts, it can still process batches that are at least 60% larger than those of other large models.